Hi, I'm Dr. Hay. In this video, we're going to find the electric potential above a ring of charge of total charge Q. So we have the electric potential due to a point charge, and we derived that from Coulomb's law. Let's look and see how this changes as we make it appropriate for an integral or a continuous distribution of charge. So we're going to add a differential on either side, dV and the changing quantity dq, or the location. Now, if we take the integral on this side and the integral on that side, k doesn't have to be in the integral because it's constant, then we just have v equals k dq over r. And now we have the equation that we need to use to find the electric potential for a continuous charge distribution. And we're going to do the example of a ring of charge, and we're going to find the electric potential above that ring of charge, a distance z. So let's draw it with radius a, and we want to find the potential at a distance z above this ring of charge. And let's say that the ring of charge has total charge q, big Q. All right, so we've drawn our ring of charge, and we have it a distance z up. This is where we want to find v. So the problem is to find v, a distance z above this ring of charge. And the ring of charge has total charge q, so total charge q. And here's one tiny bit of charge, dq. And the ring has radius a. So you can see that at all points along the ring, you are a distance, let's call it r, because it's this same r, away from dq to the point where you want to find v. So what is this r? Go ahead and compute that. The square root of z squared plus the radius a squared. At all times, that's the distance r, because it's along this ring of charge. It's not a disk, it's a ring. All right, so let's plug in what we know into the equation up here. K, and the distance turns out to be a constant. It never changes, this r, so it can come out of the integral. And what's left inside the integral? Well, it's the sum of all of the little dq's. What do the little dq's add up to? Well, they should add up to the total charge q. So this is equal to the total charge q. And so our potential due to a ring of charge above the ring of charge is k q over the distance above plus the radius squared. Now, if you didn't notice this piece, that the sum over all of the little dq's added up to the total charge q, you could also compute that with the charge density. So dq would be equal to lambda times a piece of an arc length, a, d theta, and you would integrate around theta, and you would integrate 0 to 2 pi all the way around because it's a ring. And you would also notice that the charge density, in other words, charge per line or charge per length, would be equal to the total charge over the total arc length, so 2 pi a. And once you reduce that down and take the integral, you would get the same thing as we did before.